This tutorial is for ThaumatoAnakalyptor. In it, I will show you how to download Thaumato, get it up and running, and how to do segmentations in a GUI. So first, let's head over to GitHub and to this repository. In it, you can see everything that you need. We have all our files and a good README where you can find all the information that I'm giving you right now as well again. So be sure to read the README. Here you can see the segmentation that I did last year of scroll 3, and since then the scroll segmentation tool improved steadily. You can see an overview how it extracts the sheet segmentation and also goes into the technical details a little bit. We're mainly interested in how to run the code. And for this, there are two main parts. First, we need to download some data that we want to segment. So any CT scan of a scroll is fair game here. And we also need to, well, execute a pipeline, so setting it up first. For that, we need the clone command. We need to do it recursively because there are also submodules in here. So let's do that step right now. We head over to our command line, select the path where we want to have the ThaumatoAnakalyptor installed to, and clone it. So let's go over a little bit more. When this is downloaded, you would like to install Docker because this is how we set it up, and this makes the whole dependency that there are lots of much simpler to resolve. So Docker and NVIDIA is needed, and then the runtime. After that we restart the Docker and then we can build the Docker file. So first up here, go into the downloaded GitHub repository, and then next you also need to install all these commands. I probably already have them installed, so nothing to do here, but just showing you how it's done. Copying in one via one, restarting the Docker as well. Let's do that as well here. So that's done, and now we're ready to build the Docker image. So we can copy this command. We make sure that we are inside the repository, then paste it. And before I paste it and start it, I want to adjust something here. So I already have the Docker image installed, and so I want to give this image a different name. So I do tutorial here. So it's just the name that you can use for the image that we're creating. And then this will take a lot of time, so around about 10 minutes. So I have everything already cached, but all these steps, the installation steps, run around about 1,000 seconds. So you have 15 minutes that you have to expect it to be around about. You see that it will progress over time, so that's about that. So we have it installed. Now we have this Docker image that we can use to actually run our code. All the code is already installed in there. And so the next step, when we want to run a GUI, we need to see the output, the visual output, and this xhost command does this. This pipes our display, our monitor into the Docker, and so we paste that in here, have it, and now we're already set up and running Docker almost. So right now we have everything installed, but we haven't yet had a look at what data we would like to segment. So let's head over to the data page from the Vesuvius organization. This is dl-to-text.org, and here we can go to full scrolls. I really like testing my stuff out on scroll 3, so let's do that. Go to scroll 3 vol package, and then in here you see the volumes. These are the raw scans. There are multiple ones in there, in different resolutions or intensities. I'm gonna pick this one, but every scroll volume is fine, also from different scrolls. So you can take that, and then we're gonna go down here, and there's a meta.json file. in here you can see all the information about how the scroll was scanned. So it was scanned with 53 kiloelectrovolts, and the resolution is 3.24 micrometers. There will also be some scans that have 7.91 micrometers, or maybe even different resolutions. So but this one we keep in mind, it has this resolution. Make sure to download all these files. There are commands that you can find on the website how to download a volume or even a vol package if you would like. But yeah, we need this volume here, this volume. That's the one I picked out. So let me show you. I already have this data set up here, and so here that's my volume package and volumes. So the 53, I already downloaded it. This is this one here. You can see this is a lot of images and a lot of data as well. If we go here, it's 3.1 terabyte of data, which is a lot. So the first step that Thaumato then will do is actually creating in different formats that it can better handle. Okay, so we know our volume that we want to use, and we can see here the Docker container command, which is pretty intricate if you look at it like that. So maybe this all handles running the Docker container, having the GPUs that you have available, and some RAM as well. And here the W command actually mounts some part of your file system, or also different other things, to the Docker container. So this is the path that will be available in the Docker container, so stroll.volpack. So here I just add the path to my volume package. So this one you have to choose from your Docker, from your file system. So if I have my file system like this, right, and then my path would be that part here. Let's now start the GUI. So first we make sure to have the right forwarding of the Docker to the screen, and then this one is the command that is needed to be adjusted to run the Docker image. So first up, the name, I had it as a tutorial, Docker Thaumato image tutorial, and then we need to know additional alternative scroll package path, so delete that one and adjust this part here. So from before we know that our volume package lives at this path, so let's paste in here media Julian 1p horec.vol package, and we're ready to start the Docker container. Alright, so this is now already started. We have everything inside here. Next step is actually now running the GUI. So here, start that one, copy, paste, and this should start the GUI. Give it a minute. Here it is in all its glory. So we don't have to look at the command line segmentation here, and yeah, this all is not important for us. So here you can actually see the configuration. So this is the first thing you always have to do when starting a new segmentation. Click config, and then you can fill out this stuff here. There's always this information button on every step of the way where it tells you what you exactly have to do. So here the canonical original 2D diff files are the ones that we selected before that we now have to select. So click here and search for your path. So we had it mounted at scroll.volpack. So here, then we know volumes, and the 53 here is the one that we selected. So choose. Okay, that's the first step done. So canonical render volume, you can leave that one empty, or you can set it to the path that you would like to have for rendering. So this can be grid cells or a SAR file. These are different formats that you can store the data in, so let's not go too much into detail for that, because this is rendering and not like segmenting. So this is it's downward step. So we have our scroll here, and we are looking at our meta file where we see this 3 micrometer for our data. This is gonna get important now, since we have a downsample factor. So you need to enter the downsample factor, which downsamples your resolution to something close to 8 micrometers, because that's the resolution Thaumato works at. So if we have 3.24 micrometers and the one here, the standard one, is 8 or more, like 7.91, factor of 2 might be good. Also, if you put an educative number, you can set some more paths that otherwise just are calculated randomly. So here, let's do this. We can set the 2, and then you see these 2 are actually, some of them are grayed out, or we can set the -2 and then they are not grayed out anymore. But let's put it at this. So downsample 2D diffs. This is a path where you store your downsampled 2D diffs. Okay. I already computed everything, so I can just check it here, or otherwise you could just make a new folder and do like 2D diffs, I don't know, downsampled, something like that, right? Okay. We can also check out that one. Then you have your grids, grid cells, which is the format the data is transformed into, selected. But yeah, let's stick to the one that I already computed to make this go faster here. Okay. Then surface point path. This is the path where your surface points are gonna get stored to. So usually you go to wall package under working, and then you can make a scroll surface points folder, something like that. Scroll 3 here. You can choose that one. I already computed all these informations, because yeah, it's taking a lot of time. Then here, number threads, enter the number of threads for pre-processing. This is for downsampling. I would suggest something depending on your system between 1 and maybe 8 threads is nice. Also GPUs. Well, you need GPUs to do calculations for lots of things. Just use all your GPUs that you have available. So number of GPUs you have. I have got 1 on my system, so it's a 1 here. Batch size, that depends. It's for the GPU processing, which is done in batches. Yeah, if you run out of memory, lower the batch size. And then threading, this is used for texturing. This is the same as the rendering. Texturing, rendering is a little bit called interchangeably. We leave that one for right now like this. Okay. So right now it's white here. But we have all our configs stored that we need. So let's close Thaumato again and open it again. And now, when we open it, we should actually see the scroll loaded in here. So let me make this big. And also we already have this red dot loaded in here, which is the umbilicus. So this is the center of the scroll. Let's go in here a little more. Okay. So this follows where the center of the scroll is. Yeah. This is the first one of the first steps that has to be done. Not the very first one, but one of the first. So let's now go into how to use this tool. First up, you can see lots of things over here. And these are the processing steps. You would run them in order. So you would start with the first one. You see there are some sub-steps, generating grid cells. So this is going to downsample your original data and generates the grid cells. Also important to note, if we run this here and this one here, you will see lots of outputs when I do this here. So if I press compute, it will do things here. It already detects that all my grid cells are already computed, so it skips them. I can always click stop here and then start the compute again later on. It detects the progress that you've already made. So yeah, that's one of the parts. Grid blocks have been generated, done waiting, computation process stopped. So I guess it stopped here. Now you can click a compute again instead of stop, but yeah, we are not interested in that. So we have our data. Let's look at the data. What did it create? So in the volumes, you have this 2D grid cells in the micrometers, 8 micrometers, and there's the TIFFs and then the grids. That one, yeah, it's not needed. Yeah, but we have those. So these are just downsampled images, right? If you look at them here, it's the same scroll, but just downsampled to something close to 8 micrometers. And this then is used to do the grid cells. Grid cells are 3D TIFFs instead of 2D TIFFs, and they are used for better accessing in some smaller region of the scroll. It's faster. That's the format that Thaumato works with. So we have created that. Nice. This format can also be used for texturing later on, by the way. Okay, so you can see this umbilicus text here. If we go here, that's the next step. So umbilicus. If you're clicking inform, if you hold for it, then it tells you some information, like if you have an umbilicus, you can load it, and yeah, that stuff. So let's generate one. Here we see this is the umbilicus tool. There's always the information to help again. You can use A and D, and Control A and Control D to switch to the next annotated slice. So this is a really simple process, and you don't have to annotate every step or every slice. So we do every 100 slices in this downsampled volume. Can just load. Oops, let's not do that. Load. Okay, if you click, you create a parenthesis. Yeah, but so load, and then let's Control D to the first annotated slice, which would be this one. And if you just go further around, you can see no slices with A and D. But if I click Control D again, it's somewhere here. It's a process of like 5 minutes to actually update the scroll, and always click in the middle. So yeah, you see that's like, I don't know, 10 annotated slices is enough over the whole scroll. So if you have done that, you can click save, and after you click save, only then close the window again. So this is the second step done. At this first step, that takes a lot of time. So if you don't need to do a factored downsampling, you can actually use the grid cells online. So here, if we used the 51, this would be in 8 micrometer the data. Here you can see 8 micrometer. Then we wouldn't need to do downsampling, so the factor in the config file would be 1. And we could just download the grid cells here, so the 51 grid cells. We could just download these. That would speed up the process a lot. Also, if you don't want to run computation of the whole scroll, like I have all the grids in here, you can just paste the grid cells that you're interested to run the computation on in here and leave all the other ones out. And then you have a faster computation later down the road. Okay, so we've created the grid cells, the umbilicus, and we also selected only the region that we're interested in by only pasting the 3D TIFFs, grid cell TIFFs into the folder. Now we can run the point clouds. So also there is computation happening, and the compute that you already did will be tracked. So if you stop and start again, you can just pick off very left, unless you want to do recompute, and you click this button here, but yeah, we don't want to do that. Okay, so compute. You will also see again here stuff about the process, what that it's doing. Yeah, it does some things here, and also when you see it's finished computing, then it just stops. Yeah, I guess that's that part. Then next steps would be instances. So point cloud takes maybe a day to a few days, depending on the scroll volume that you do and the amount of data it has to crunch and your system. And these steps again, very compute intensive. So it's the instances. So you start it, and it creates your instances. I'm gonna stop this again here, but also takes a lot of time. Yeah, so after you created your point clouds and your instances, you're already now set up to actually do meshing and well, segmentation in general. So let's go in here. There are two main steps, which are sheet stitching and meshing. So sheet stitching is actually the actual segmentation where you extract the surface, and with meshing you make a computer representation that's easy to interpret for the computer from this segmentation. So I've created my point clouds, and there's something neat that I can do now. If I click display point clouds, I will see the point clouds. So here you can see all the blue dots are the point clouds, the points of the point clouds that you created, which show the front side of the surface. We're interested in the front side. Now at this point, if something went wrong, you would see that your points aren't lining up properly. They aren't on the front side of the sheet, or there are lots of missing parts, or points in the middle of nowhere, or just something went wrong, and you would see it here. So be sure to check that one out. Okay, so yeah, you can also make it make them display or not display. At this point it doesn't matter. So the next thing is sheet stitching. Here let's fill out all these things with random values, with default values first. Something that's really interesting is selecting a starting point. So there is a bug where you only can select the starting point inside the green triangle. So I might want to segment this sheet here. So I set my starting point here. So that's the green point. It already also selected it here and filled in the information. Now the next, I click again and now I have my same mouse again. Now the next thing that's really interesting is the K range. This is counting how many times the segment that you're creating should go around the umbilicus and in which direction. So -1 means it goes, so it goes inclusive, like K from inclusive -1 to 1. So I have -1, 0 and 1, which will be our range. So if I have -1 and 1, so it will do the winding we're on right now, and then one more in both directions. Sheet Z range is again the same for just the Z range of your segment, how tall your segment should be. You can just leave it at 0 and 40,000, which would mean just a complete scroll. Then something interesting here is the winding direction. You have to set it based on which scroll you're working on and how it is wound around the umbilicus, which direction. So for scroll 1 the orientation would be -1, and for scroll 3 it would be 1. And so if you have a different scroll, you would have to compare the winding direction to those two scrolls and which one it would line up with. Yeah, these other things you can just leave them. And so if you've never done this segment, you can just leave those empty. You would never actually use this recompute button, I guess, but the continuous segmentation you would use. So yeah, let's start the computation again. So have this one here. This is all stopped. Now we want to compute the segment. You cannot actually see the compute here, but here. So the first time you start any segment with a new scroll that you did, it will do some pre-processing to build a graph, which it then tries to solve to go to the segmentation, which takes around about an hour. But you only have to do it once, and after that the segmentation should be quite fast. So here right now it loads all the data it needs. That takes a moment, and after that it will start the segmentation. So you can do multiple segmentation runs with the same starting point, and then you can just iteratively grow your segment. So right now we have 3 wraps around the center that we are doing, and it's computing that here. But if you finish this segmentation run and it actually saves the data, then you have the advantage that you can do a next segmentation on it. So let's say you want to go and add, I don't know, 3 windings in the positive direction or 2 windings. So we would go from 1 to have some overlap, so like this would be still the same overlapping segmentation, maybe from 1 to 4. So you have 3 more wraps that we would do. And then you would click the continue segmentation button and compute again, and then it would pick off where you left off last time. Okay, so I will come back to you when this is done. Okay, so it started processing of the actual segmentation. The random walks are these. It took 2 minutes to translate the data to C++, and now it runs the random walks, the actual stitching algorithm, which, yeah, you can see it's pretty fast. It's already almost done. Okay, now it's done. It saves the data, and I come back when this is done already. Alright, now the segmentation is complete, and we can move on to meshing. Important, leave those actual values in here. You have to have exactly those values in there, because the segmentations get tracked by the starting point. So if you change the starting point during your meshing, it won't track the segmentation anymore, and if you run this meshing step, it doesn't know what to mesh. So leave those in there. Let's press compute. Do it again. Takes some time. Yeah, just leave it be. Doesn't take too much time. I don't know. Yeah, maybe 5 minutes. Let's see when I come back. Okay, at this time the meshing is done, and now the flattening runs, which is also a part of the meshing. But we can also already look at the mesh that was created. So for that I use Cloud Compare, and I open the path. So here it scrolls surface points. It's in the surface points that we selected, and then this is the number, that's the starting point. Click here, and we actually have the mesh object, so let's load it in here. And there is also a materials and textures file. Disable that one, and voila, we've got our scroll data here. You can see it's a little bit tangled up, I guess. I'd say it has a lot of ups and downs in here. Yeah, so probably here that this is an interpolated part, where that is smooth. Also here you can see this is interpolated, so that's not actual data, so data was missing here, couldn't find it. Same here. So yeah, here we have no data. We can also just look at it like that and see how it wobbles in and out. So that's our scroll. The 3 windings that were created. Okay, that's nice, and I hope that the other part is also finished now. Maybe, I don't know. Which at this part I have to say, the mesh is already recreated into the original volume, which was 3 micrometer down up from this downsampled version that we had before. So if you have something to render it in the original volume, good for you. I do not have that with me here right now, so I have to actually do a little hack. So during the grid cell step here, we generated downsampled grid cells, which I will now actually use to do the rendering. So yeah, this is a hacky way. I'm gonna go back in here and do select the downsample factor of 1, because the grid cells are in this 8 micrometer data and that I want to use for rendering. And so go also to my scroll here. This is now the rendering path that I want to use. And then now I select my grid cells here, my grids. I could also use the SAR, I guess. Yeah, I can also use the SAR file. So grids or SAR. If you have no SAR file, you can use the grids. I use the grids that you also have. But SARs also work for that. Yeah, save that here. Now, because the meshing was already done and in the higher resolution, I actually have to rerun it again. And this time it creates the smaller mesh in the right size for the rendering and for the volume that we choose. So yeah, I will be back in another 5 minutes again, or 10. Alright, so the hacky meshing is now running and flattening this new mesh, and here I can show you how this new mesh looks compared to the older one. Okay, so yeah, you can see the difference between it. So this is the unscaled new version, which we have the downscaled volume for, and this I can use now to have some rendering to show you. But yeah, usually you would of course use the actual big segment in the original volume format. Perfect. So the object was successfully written. So this is the meshing step done. Leave the XYZ in. The volume swap, you wouldn't need to do this. That's only the case if you want to transform your segmentation from one volume into another. So let's say from 53 into 51 or something. Now we can go back over and do the rendering. So we can specify if we want to output our format to JPEG or TIFF. Yeah, let's do the rendering by clicking compute. This compute step should now go and also display you the progress, which would be nice if it worked. Let's see. Alright, here we go. Okay, so here you can see a live render view of the progress. And also, if you go over there, I guess you can see the time remaining for this segmentation here. So 1 minute. This won't probably be the complete 3 wraps, but in the actual use case, this segment was like this complete mesh will be split into multiple smaller meshes, so the rendering and flattening can work better. So this is probably also the case here, where we have now multiple renders that will be done. So for actually inspecting the meshes, I would recommend you a different code. So let's see if I can see. Let me just check it out. Okay, so I would recommend you use Crackle Viewer to actually see and inspect the volume that we did. Perfect. So this is Crackle Viewer. Okay. Maybe it was just writing before. So this is the segment that we have, and now I loaded it in Vesuvius Crackle Viewer. Now there's also this cool feature where we can actually average some or multiple slices. But maybe just before we do that, let's look at the segment and the quality of it. So here you can actually see lots of surface area that looks good, kind of accurate, but then also here, those region here, they just look completely like bad. So these aren't good segmentations here. But yeah, this area here, for example, all of this very good. So yeah, you can use all these areas to actually search for segments. All these are good areas, I guess. Here as well. You just have to be aware of it, that the segmentation isn't perfect. So yeah, you could really use stuff here, but then here again you can see this is switching the sheet, so and no here, for example. Yeah, here, so I wouldn't be using all of this. But yeah, then back over here we have big, good, nice area again. So yeah, just be aware of that. Maybe do something like a step where you actually only use this area that you selected beforehand. And yeah, let's actually look at the multiple layers together. So maybe 3 in each direction, so 6 layers. And look at it again. Now, if you can see this fiber stripes, it probably means it's the same sheet. So here we have the same sheet. Also here, I guess. But then here probably it switches sheets. So yeah, here's not such good area, I guess. Yeah, then for sure here again, you see that it's switching. But over here again, you see the sheets that the fibers align well with. So yeah, you have to kind of be aware of it. Look for the areas where the fibers align well, and yeah, pick those areas to run your ink detection models on, or anything that you want. Yeah. Yeah, that's around about it from Thaumato. I hope you enjoyed this tutorial and learned something from it. And yeah, please use Thaumato in whatever way you can, and if you find something that you really do not like and you know how to improve it, just improve it and make a PR. We're very open to improvements to Thaumato in any way whatsoever. And yeah, maybe you can win a progress prize or even the first automatic segmentation prize. I wish you all good luck and have fun with this tool.